energy particles. Okay, so on one side of your little thing here, okay, label more energy. Right here on this side, label less energy. And really, it's energy per photon. Right, so you could say more energy per photon. Right. So at the beginning, and notice the time scale. Right, 10 to the minus 35th seconds. Halfway across, we're only at 10 to the minus 4th seconds. And then this is like 1 second is halfway across, and now it's like 10 to the 10th years, right? Okay, so that's our time scale here. Our time scale is a little bit warped, but all the good stuff happened there, right? There we have it, right? Okay, now here is a weird thing. As you go this way, the universe expands. Okay, now as you expand photons, they lose energy. You start off with things like gamma rays, which could be used to sterilize meat, maybe, right? And as you stretch them, they become ultraviolet. Well, that can give you a sunburn, but it doesn't kill you, correct? Right? Then it turns into maybe infrared, which is a longer wavelength, which just sort of warms you up. Then it becomes microwaves if you stretch it some more, and then it becomes radio waves, et cetera, right? So these things become less energetic as you go this way, right? Now, let's go back to this idea. If you have enough energy, you can create matter. But the deal is you have to create matter and antimatter. Right? So this guy is antimatter. This guy's matter if this is an electron. Right? So this is called a positron. And right now, in the cabinet behind Matthew, there's radioactive elements that are undergoing something called beta plus decay. And when they undergo beta plus decay, they create a positron, which is an antimatter electron. Right? Now what happens when a positron meets an electron? What do? This is true. If you're a Star Trek fan, right? It's true what happens when matter meets antimatter. What happens? They do that again. What happens? It blows up. It explodes. Now here's the crazy thing, right? What these guys are going to do is we never ever, I don't believe we ever find positrons. They can't make it into our detectors because our detectors are made of matter, and matter has electrons in it, right? So what these guys do, this positron is just going to basically run into an electron, and then it's going to create a pair of photons, right? These photons run off and make matter, et cetera, et cetera. Okay? But there's this process where energy, photons of energy, create matter. The antimatter annihilates. It creates energy. Energy creates matter. The matter creates energy. Yes? Okay? And what we think happened back in the Big Bang, okay, is that all of these hadrons are very heavy things, like protons are the lightest hadron, right? So where it says hadron era, draw a little line here, okay, and just say this is the energy to create a proton and an antiproton. Before this point, right, so where it says hadron era, put a little label there and write, this is the energy to create a proton and an antiproton. Yes? All protons that ever existed were created before that point, and after that point, they weren't created because there's not enough energy to do it. Yeah? This has more energy here, doesn't it? This has less energy. This threshold here is the lowest energy they can have to create a proton-antiproton pair. So if you can't make them anymore, what do they do? What are all the protons going to do with all the antiprotons? They're what? They're going to go to them, and what's going to happen? They're going to destroy each other and become photons, and maybe never ever make protons or antiprotons again, right? So here's one of the questions, and this is a lingering question of the Big Bang, is, and I think this is a philosophical question, right? Why is there something rather than nothing? If during this whole thing, where photons were creating matter and antimatter, if it created equal parts matter and antimatter, why, when it all settled down, is there something left? Yeah? It should have, if it created equal parts, there should be nothing left, correct? We should just have a bunch of big photons running around in empty space, but there's something, right? I think it's Nietzsche that said, why is there something rather than nothing, right? You know? And then the other question you could ask, and this is somewhat less serious, right, is what if it's really antimatter that we're left with? that's funny because obviously what's left we called matter, but anyway, yeah. Okay. Now, let's go down. Protons, what's more massive, a proton or an electron? Protons are they're 2,000 times as massive as electrons, right? And so now when it says lepton, okay, see where it says lepton era? Remember the lepton era? Oh yeah, I remember that. That was up until 10 seconds. That was a great time, yeah? Oh, I remember the lepton era. Okay, in the lepton era, now we can no longer make hadrons. We can no longer make protons anymore. So all the protons that we ever had, they stopped making them here. They stopped making them back then, right? That's why they're so valuable now, right? Okay, now, if you go forward, electrons are a lot easier to make. It takes much less energy to make an electron, right? Well, at this point, you can no longer make, now it's the energy to create electron positron pair, right? It's the energy to create an electron positron. And again, when it all settled out, we stopped making electrons and positrons. And when it all settled out, this is like condensation, right? The temperature drops, things condense out. We can no longer make hadrons, which are just protons, big word for protons, right? And there's a lot of hadrons, by the way, but they all decay, at least all the baryons decay to protons, I believe, right? And then there's 3 different leptons, okay? But the electrons are the only stable ones. Everything else decays to something more like an electron, right? Now once you've made all the electrons, right, then they condense out. Now you've got plasma, right? This whole thing here is plasma, right? So now you can draw plasma. What is plasma? Plasma is protons and electrons buzzing around, but they're not bound to each other. You've got atoms. In fact, a proton is the nucleus of a hydrogen atom, correct? Yes. Okay. You've got atoms, but they are not bound. The electrons are not bound to the nucleus, right? Isn't that what plasma is? Did we talk about that? Yeah, plasma is a state of matter where the electrons are all free, and they are not bound to the... I do. Somewhere. I've got too many things in this pocket. Oh, that.
Yeah, thank you.
Okay, now, what is true about plasma? Plasma, yeah, generally we find plasma in something that's really hot. Okay, does plasma conduct electricity? Yes, it does, because it's got all those electrons and protons and whatever are free. All the nuclei, all the electrons are free to move, and they do move around. Okay, and since they can move, it conducts electricity. Do things that conduct electricity allow light to travel freely through it? No, they don't. So here's the crazy thing, right? Okay, so when you look at the sun, if you look at the sun today, if it ever comes out from behind the clouds and you stare directly into it, don't look at the sun, right? But if you ever do that, understand that the photons that you see now that are released from that surface of the sun, it actually took them 10,000 years to percolate their way from the core of the sun where they were created. They bounced around because the sun is plasma. Light cannot travel the speed of light through plasma. It just bumps, the photons bump around like particles in a soup kind of moving around, right? And eventually they get to the surface and they're free, okay? So the sun is opaque. That's the crazy thing. We get the radiation not from the core directly, but we get it from the surface. Neutrinos, little particles that don't interact with matter, that figure prominently in the movie 2012, those come from the core of the sun, and we can see them, all right, directly. Well, they're very hard to detect, right? But this is plasma. Now, isn't it true that up until this point, right, and by the way, correct that, it says 500,000 years. Change this to 0.37 times 10 to the 6th years. It's 0.37 million years, okay? So correct that number there, okay? Up until this point, the universe is opaque. Yeah? The universe is opaque, and actually, at this point, something happens that makes it not opaque and that makes light travel freely. What do you suppose that is? The what? Big Bang? That happened here. This is bang. What about plasma makes it opaque? The electrons are free, correct? Yeah. Here they must not be free. Where are they? What are they doing? Why are the electrons not free? Are they attached to the protons now? Yeah. So here's why. Right now there's enough energy. Every collision between particles frees all the electrons. There's enough energy to free all the electrons. Now suddenly there's not even enough energy to free electrons, right? So this is the universe